right, so yes, my name is Jenni Raitoharju, and I will continue with a bit similar theme, but now using machine learning in biomonitoring. And when I was trying to think what to talk about, I had a bit of problem to decide since I had my defense in 2017. I've been working with at least all these applications and different machine learning methods, mainly guiding the students in different projects. But this has been very nice to be involved in so many things, but then again, I don't have so much time for my own personal research. Anyway, I decided to take this biomonitoring out from there. It kind of allows me to talk about these machine learning methods from very simple point of view without any technical details, and maybe show a bit how we can use some of these techniques and a bit of the problems we face. In general, we would like to concentrate on doing research on these methods and theories, but in practice we get the funding from the application side, so then we try to find some kind of balance between these two sides in our group. So specifically, or mostly, I will talk about these benthic macroinvertebrates. They are these tiny creatures that live in the bottoms of lakes and rivers, even if everything is fine. But they're very important because the kinds of macroinvertebrates and how many of each kind you find in a specific lake, it tells a lot about the quality and ecosystem state there, and they can indicate any potential environmental problems before anything. You cannot measure from the water these changes yet. So this is why there's this European Union legislation that tells that you have to regularly collect these creatures and count what you find. And of course, this is very hard work. It requires these highly trained experts who can recognize these things, and it can be very slow. Sometimes they can use 45 minutes to examine one bug. And yes, and of course it's kind of boring job. They just take one after each other and try to give a name to it. So this would be something that would be very nice to automate. And we have had this project, Academy of Finland project, since 2015, where we want to do this. We have been collaborating with this Finnish Environment Institute, who actually is responsible for this monitoring. Also from Jyväskylä University, they were doing some imaging things and statistical analysis, and we concentrated on these machine learning methods here. So we want to make this process as automatic as possible, and of course we would start with using these deep neural networks that they have everywhere nowadays. So this goes to very basics. So what do you need to know about these deep neural networks? Of course, you need to train them to do the task, and they always learn from these examples. If you want them to recognize cats, you have to have many images. This is a cat, this is a cat, and it has to be labeled in the sense that not just images of cats, but also with this information that this is cat. And basically, these networks, they are very stupid. They only realize what is shown to them, so they don't really understand what is important there. So for example, if you would have, when you take your cat pictures, you would have a tiny dirt in the camera lens. And next day you would wipe your lens clean, but take pictures of dogs. Then this network would learn to recognize this. All these pictures with this tiny dirt there, they are cats. This is the easy thing, so I don't need to learn anything else. And then you would not get very good results, because then when you take pictures of cats next time, it would fail. So you need lots of data to show the different variations of these different species. But also with here, it's not good that it's too varying the pictures. So for example, if you want to learn to recognize these insects, it's a much easier task if you take pictures of them with clean backgrounds compared to this situation that you take them in the natural environment, and then you would need like millions of pictures to learn to first pick the insect from the picture and afterwards recognize the correct species. So there has to be some kind of balance between this. And this is also why it's very difficult to use data from other sources. So if we have a similar data set in Germany, but they have a bit different imaging conditions, then the network would just learn that, okay, these species are the ones with this background and this camera more than the actual important things in the insect itself. And one more thing is that what this network learns is a specific criterion. So usually you would require it to have this high classification accuracy, but it has to make sense. So if you have 99.5% of your images from one class and only 0.5% from the other, and you tell to maximize the accuracy, it would of course learn to put everything to this one class, and it's 99.5% accuracy already. So there's like no point to try to go better than that. But in this case, of course, probably the 0.5% would be the most interesting part. So you would need something else. So then we started collecting these pictures of these macroinvertebrates. This is from upside the image. So we have two perpendicular cameras and we had a glass tube. We are dropping each insect there and taking pictures from these two cameras at the same time while it's falling to the bottom. And then we can drop as long as this bottom gets filled, and then we empty the cup and take more pictures and so on. This was not done by us, but the Jyväskylä collaborators. So what they did, they actually got a total of 2 million images with actually some biologists labeling them, and they came from 130 different classes. But there are some problems. So far we have been able to use about 500,000 images from 39 classes because the camera was changing and so on, so they are not so straightforward usable, the rest of them. And now we have always like 50 images of the same macroinvertebrate. So while it's falling, the cameras are taking pictures and we are using all these images to try to recognize it. And here I've listed some of the special challenges then what we had after we got this data. First of all, this is very fine-grained. It means that these different specimens, they are very similar. Like even though I have seen them a lot, I cannot distinguish even between the two different kinds of species. So it has to be something very detailed how they are distinguished. Then we had a problem with the imaging or the image size, because these neural networks, they take the certain size of image as an input, but these Jyväskylä guys, they were not so familiar with these techniques, so they decided that since most of this is just the empty background, so we can get rid of it and save a lot of space, so they cropped each insect out of the background, so every image has a different size, and this was a bit of a problem for us. Also, there was some imaging conditions were changing. They changed the camera, they changed the light bulb, but with a bit different color, or they changed the liquid in the tube. And all these changed the background enough to cause some trouble for us. Then the labeling is hierarchical. So we have this order, family, species level differently, but we told these biologists to classify as well as they can, so to the most specific level. But of course they had different skills, and we have varying levels of hierarchy in the labeling. And of course this is very unbalanced. There are lots of the most common ones, and then a bigger problem is that these rare ones are of course the most interesting ones that they want to classify with most detail. An even bigger problem is that these unseen classes that we don't have yet, they are of course the ones that we need to find out as soon as they come to Finland. They might come from Germany, but how do we recognize them when we don't even have any pictures of them yet? So something to deal with. Yes, we have multiple images. And then of course we have practical problems like these. Biologists are not really willing to trust these methods even if the accuracy is high. And in the future we need to consider genetic methods, but nothing more about that. These colors kind of show which of these challenges we have so far considered. The blue ones, the red ones we haven't touched really yet, and the purple one we have kind of started looking into, but not really deep. This is some of the images from different classes now. So here you can see how similar they are between each other, and on the other hand, how there can be this variation within the class. This is the labeling. So the innermost circle shows the order level. We have 7 different orders, as you see, or actually you don't see because you see only 5 of them. So this shows that 2 of these 7 are very rare. We have like some, let's say 2,000 images among these 500,000 that we are looking into. So they're very rare in the data set. Some of the works we have recently done on this topic, we had a competition against the human experts organized by this Finnish Environment Institute. And we also compared how to take this hierarchy into account. So some conclusions is that we are still not where the human experts are in terms of accuracy, but we can outperform the human experts if they are told to use images only. So of course they use microscopes and they might pull X out and all these things to make better predictions. So, and of course anyone who's not an expert on this would of course not perform as good as the machines. Maybe I'll just go to the next one. So this was then about evaluating how confident we are in the machine prediction. So it's not your output, it's not just the class, but also kind of how many percent this neural network thinks that it's a certain class. And we made some research on how to evaluate this confidence. And then since we had 50 images per specimen, so how is it best to combine these different predictions? Because it's possible that some ankles are very good for predicting and others are not. And also, how can we then evaluate the final confidence after taking into account all these 50 images? So this was quite good. So it correlates a lot. We get basically 100% accuracy for 40% of the images. So this is something we can tell to the biologists, that if you set the threshold there, then you can kind of be sure that this is correct, and then you can do the rest if you don't trust the neural network. Or you can set the 99% accuracy somewhere 70% of the bugs classified. So this would help them a lot already to move towards this autonomy, and then they would just classify the most difficult cases. The data imbalance question we have considered a bit, but so here you of course need to think how to even evaluate it. So if you just use the accuracy, it will not care if the tiny classes go wrong. So somehow you need to weight these tiny classes more. And the same with the training of the network. You have to make the network concentrate on the hard parts. Then you can do all kinds of tricks to produce more images. So of course you can rotate your images to have more flip, zoom in, zoom out, add some blurring. This is an easy way to do it. But then they are still kind of same than the original image in terms of the position and so on. So there are these generative adversarial networks. This is why I have the celebrity faces there. So what's specific with them is that they are not real people. This is artificial images of persons. So it's possible to produce very real-looking images with these guns, they call them. But of course it's problematic in this case, because then we have to make sure that when we produce these images, they still are from the specific class and not from the neighboring class. And these unseen classes, we have not really applied this for this biomonitoring yet, but we have some other works. So this is called, for example, one-class classification. You only use samples from a single class, like cats. You only have pictures of cats, but you want to make some kind of model of this, so that if a dog comes, the model would tell that this is not a dog anymore. Or that they call it novelty detection, where you can have multiple classes, but whenever something is so different from what you have seen already, it would tell that, no, this is probably a new class. And then I'm getting almost to the end. Quickly about these extensions of the work. We have collaborated a lot with Aarhus University. They actually took the imaging device that we were using for our data set, and they had this robotics project there where they don't have to manually drop the samples anymore, but they have this robot that will pick the macroinvertebrates and put them to the tube, and the cameras will take the pictures automatically. So this will really make it faster in the future. And we have together with them also this project in Greenland. They have like a few hundred of pictures there where they want to know how this flowering season is changing due to climate change. This is very remote areas of Greenland. But these cameras are taking pictures like every 10 seconds there. This way you will have millions of images, but what they want to know is that how much there are flowers, how many of these visitors, pollinators come there, and when it's like, basically just to use this information to define the flowering season length. But of course this is something they could not do manually, so this has to be done automatically. So this is then some of the conclusions for using machine learning in biomonitoring. This, of course, allows these human experts to concentrate on these actions that should be taken instead of just monotonically labeling the insects. And this can make it much faster, since this takes few seconds, not 45 minutes per bug. And of course, this way you can also cover a lot higher number of these macroinvertebrates, which would make it a lot more reliable, the conclusions that you make based on that. And this allows some biomonitoring things that were not possible before, like this Greenland thing, because there are just too many images for anyone to manually go through and check. But machines can do it. So this was the end of my presentation.